Throughout the next two videos, we'll be focusing on writing the equation of a polynomial function by using finite differences and then linear regression. This particular video will focus on what finite differences are, and then in the part 2 video, we'll focus on how we can use linear regression on our graphing calculators to actually find an equation to represent this particular situation. So before we can actually talk about using finite differences, we have to talk about what finite differences actually are. So finite differences occur when the x values in a data set are equally spaced out. So you'll notice here that all of our x values are equally spaced out and we're adding 1 to each one. So we need to have that piece first. If you do not have equally spaced out x values, finite differences will not work. We won't be able to utilize it. Secondly, when we're using finite differences, we're focusing on the y value differences. So it says the differences of consecutive y values are called finite differences. So let's find the finite differences for these values on the screen. When I do this, I notice that I'm going to take the later y value, which in this case is 4, and I'm going to subtract from it the 9. So 4 minus 9 makes this finite difference between these two values negative 5. I then take 1 minus 4, which makes this finite difference negative 3. I then take 0 minus 1, which is negative 1. 1 minus 0, which is 1. 4 minus 1, which is 3. And 9 minus 4, which is 5. So as we're finding finite differences, we can actually find different layers of finite differences. This difference, being the first one between the first layer of y values, is called the first difference. And then from here, because there's still differences between those values that are related to the y values, we can go to another layer. So as long as there's a difference, we can keep going. So here now we would take negative 3 and we would subtract a negative 5 from it. Well, negative 3 minus negative 5 becomes negative 3 plus 5, so that becomes 2. Then I have negative 1 minus negative 3. So negative 1 minus negative 3, that becomes negative 1 plus 3, and that becomes 2. 1 minus negative 1, well, it becomes 1 plus 1, so that one is 2. 3 minus 1 is 2. 5 minus 3 is 2. So this here is called our second difference. Now, because in this case they all became the same value, that's really as far as we can go. However, there are situations like cubic and quartic functions where we can keep going to a third difference or a fourth difference or something like that. So this is telling us that we have a quadratic or a parabola graph, and we'll talk about that pattern on the next slide. But the important thing here is that you understand what a finite difference is. It's when we're looking at the y values, when our x values are consecutive, and we're finding the differences between those y values and looking at the patterns that result. So what's really cool about finite differences is there's actually a pattern between finite differences and the type of equation that we have. So I'm going to show you here how we can use finite differences to determine what degree our polynomial actually is. And here it states that if a polynomial function f of x has degree n, then the nth difference, so that means you can go first difference, second difference, third difference, fourth difference. The nth difference of the function values for equally spaced x values are going to be non-zero and constant. So on the last slide, that was when we saw 2, 2, 2, 2. Now the reason I wrote and vice versa here was simply to give myself more space. You can also apply this property in reverse, saying that if you have equally spaced x values and that your nth difference has a constant non-zero value, such as like 2, 2, 2, 2, because it's the nth difference, we can then tell that this particular polynomial is an nth degree. So here we can notice that we have x values that are equally spaced out. They are all 1 apart. So what we're going to do now is we're going to look at the finite differences here and see if we can figure out what degree this particular function really is. So remember, we start with 4, and we're going to subtract 1, so the finite difference there is 3. 10 minus 4 is 6. 20 minus 10 is 10. 35 minus 20 is 15. 56 minus 35 is 21. And 84 minus 56 is 28. So this is what's called our first difference. So we can see for a fact, because these are not a constant non-zero, that this is not a first degree polynomial. So we're going to move down now to another layer. We're going to look here. So here we have 6 minus 3 is 3. 10 minus 6 is 4. 15 minus 10 is 5. 21 minus 15 is 6. 28 minus 21 is 7. So this is our second difference. And we notice that, again, this is not a non-zero constant number. They are all different numbers, so this isn't quite a second degree polynomial either. So now we can take this another layer, and we can see what the third difference is. So 4 minus 3 is 1, 5 minus 4 is 1, 6 minus 5 is 1, 7 minus 6 is 1. So our third difference here is resulting in what's called a non-zero constant. 1, 1, 1, 1. It's non-zero and it's consistent. It's the same value. So because this is the third difference, this is telling us that we have a third degree polynomial, which, because third degree is we're cubing something, this is called a cubic function. Now, if you notice that it wasn't until the fourth degree that we had something, that would be called a quartic. And then if we had a fifth degree, that is actually called a quintic. Now, you don't really need to know beyond that, but just being aware of those names so that we can utilize them when needed. But this one in particular, because it's a third difference, is a third degree polynomial, and it is called a cubic. And we're now going to use this information tied together with linear regression in the next video in order to actually create an equation using this particular table of values.